Section 5.5, the alternating series. The alternating series is different from what we've done so far in that what we have done says that we have a bunch of positive terms. Okay, so far basically everything we did says something about being a and being positive. Now the alternating series means means everything, the sign changes. For example, the alternating harmonic series, we have 1 minus 1/2 plus 1/3 minus 1/4 and so on. As you can see here, that is the alternating series is it can be alternating in two basic ways. It can start out with a positive term or start out with a negative term, and then it alternates forever. Okay, now if that is the case, it has to alternate like that all the time. If it doesn't, then if it plus for a while and then minus for a while and then plus or whatever, that's not the alternating series. So the alternating series we're talking about is really specific. That is, it changes every single term. Okay, and then if that is the case, we will define it as the alternating series, and then we are going to let's see. The first thing we're going to do is calculate the alternating harmonic series. Now, the alternating series always have a -1 to some kind to the power n or n plus 1. The purpose of that is to control the sign. Okay, that's the switch. The switch is the sign from plus to negative. So now we have the harmonic series. We're going to figure out what it is. Now the harmonic the alternating harmonic series. Now the regular harmonic series, that is with all the plus signs, as we know, add up, diverges to infinity, even though it does it very, very slowly. Now the alternating one, however, doesn't diverge. It actually converges, and we're going to prove that right now. The way we prove it is go in detail, actually, is first we consider the odd terms. What's the odd term? That is s of 2k plus 1 to the partial sum. What is s of 2k plus 1? Then it equals to now s of 2k plus 1 by definition would be s of 2k minus 1. Okay, we go 2 terms back, so that's the 2 terms before, and then you will minus 1 over 2k because the even terms are negative. See, and then plus the next 2k plus 1. Okay, so you see it lined up to be the next sum, which partial sum, which is 2k plus 1. And what is that? Now, being that this value is this is bigger than that, so this value is less than 0. I mean, counting the minus sign. So when you add it together, then it becomes less than s of 2k plus 2k minus 1. It's going to be less than this term itself because you reduced yourself here. So being that this sequence is bigger than its previous, all the odd sequence is bigger than its previous term, that means this is a decreasing sequence. So we know that this is decreasing. So s2k plus 1 is decreasing. So where we're going with this, we're heading for the monotone convergence theorem. So the next thing we need to prove that is bounded. How do we know it's bounded? We can write it like this. Write out the original sequence. The partial sums is the original definition. I mean, of the partial sum is the alternating harmonic series, and therefore is called, but we'll write it like this. We'll write down something subtracted by itself. Okay, so we'll start with 1 minus 1/2, and then the plus, the next thing 1/3 minus 1/4, etc. So very quickly you notice that if you group it up like this, each time you have something that's positive. This is positive, right? And this is also positive. Each time you have something subtracted by the fraction that's slightly smaller, so it's all positive. Therefore, sk2 plus 1 is going to be bigger than 0 because it's a bunch of positive stuff added together. Therefore, it's bounded below by 0. So sk plus 1 is a decreasing sequence that is bounded by 0, and therefore is by the monotone convergence theorem, this thing converges. So sk S2k plus 1 converges. Now the exact same argument in the different direction can be applied with S2k. Now S2k, if we did the same thing, it will equal to something like this, except that it's the signs are opposite. It might, instead of decreasing, it is increasing because of some details. Okay, then, but in any case, it get S2k. Yeah, this becomes a plus. Okay, and then this becomes a minus. Then if you get plus or minus, then it actually becomes an increasing sequence. And then a similar thing applies. Then S2k is bounded on top instead of on below. It's bounded on top. If you write out a very similar situation. See, the first term is S2k is, if you write it out, is bigger than the previous one instead of smaller. And then S2k is bounded by 1 because it's less than 1 because it started 1 and then it's subtracted by each time it got subtracted by a small amount as it adds up, as things get summed up, so it end up being less than 1. And so by the same argument, almost identical argument with opposite signs, then S2k also converges. As a result, then, so the last step we're going to argue is that the limit of S2k equals to, okay, so by definition, then S2k plus 1 is the same as S2k, okay, which is the sum before, and then add one more term. Add 2k plus 1, and therefore the limit of this thing, you slap the limit sign on there, it doesn't, everything applies. So therefore limit k goes to infinity of S2k plus 1 is, we'll write all this stuff out. Limit k goes to infinity, S2k plus the limit of 2k plus 1. All right. And so what is this limit? Well, whatever it is, we'll call this limit equal to, all right, we'll call this limit S. We'll call this limit S. And notice that over here, the limit as k goes to infinity of 2k plus 1, that's just 0. So this goes to 0, which by this equation, then this has to also equal to S. Okay, so the odd and even partial sums are approaching the exact same limit. Now at this point, then we argue that by the definition of limits, then the entire sum, that is the entire sequence, so the regular sequence, then it is the same as also converges as the limit as n goes to infinity. The regular sequence it also goes to S. The way the book hasn't explained why that is. What you do is that you can the regular limit, then you can choose it to be you can choose, for example, going by the epsilon definition. So given epsilon, okay, you can choose n1 that corresponds to the first sequence, where for big enough k, then as the first sequence 2k plus 1 plus 1 would be within minus s is within the epsilon. And then you do this, then you choose another n2 for the even sequence S2k, which is less than epsilon. And then the and then the regular sequence, then you just pick the one that's bigger, then for the one for the bigger n, then by the triangular argument, then so choose if n is bigger than n1 and n2, then for that, choose that. Then so for n bigger than this particular n, then the sum Sn will be within the S will be within the epsilon. I think it's called a triangular argument or something. If you think about this, it'll make sense, although the book hasn't bothered to even to show that argument. But yeah, that should be good enough. And so anyway, so that we that's how we prove the alternating harmonic series does converge, is because both sequences, both partial sums, the odd and even term, both converge to the same thing. Now, and then there is, however, a graphic demonstration why that is true, okay, which is on your book on the next page, where you can see the demonstration of it. The graphics demonstration what that means is that, let's say you start at 0, okay? So when you do +1, you walk all the way to 1, that's S1, right? And then the second time you -2, so you walk backwards. See, over here, so you walk back to S2. And then you walk forward, then you have the +1/3, you walk forward to S3, and then you walk back to S4, and you keep walking. As you can see, each time you turn direction, you walk a shorter distance. So you got stuck in here, okay? There's no way you can ever get out, see? Because each time before you break out the previous boundary, you already turned around, because the harmonic series, the terms decreases each time, right? Each alternating means you reduce by less. So as you can see, you're gonna zoom in at some point. Is you're just gonna walk less and less, and eventually you're forced to you're gonna be stuck in a very small area. So that is the intuitive way why the harmonic series is the alternating harmonic series is bounded. And then the next thing is the alternating series test. Now, what we just did is similar to not just the alternating harmonic series, but alternating series in general. If it fits certain conditions that's similar to the harmonic series, then the series will converge, and that is actually how it's proven. But we proved it with a specific example so that things look simpler. But the general proof for alternating series is the same. That the test says, this is on page 498, that if you have a alternating series as defined earlier, that is, you have things goes plus minus, doesn't matter if you start with a plus or start with a minus. The point is you guarantee to go plus minus without exceptions. So such a series converges if two conditions. Number one, the bn has to be bigger than bn plus 1. That is, without considering the sign, this term has to be bigger than that one, and this has to be bigger than that one. Each term has to be bigger than the following one, okay? Or equal to. Equal to is okay. It has to be bigger than or equal to. And then secondly, the limit of this thing as it goes to infinity, the terms has to go to 0. And you might think at first that, well, if the limit goes to 0, obviously the terms are going to be bigger, right? Not necessarily. You can actually arrange it so that something always jump up a little bit, and then it goes down. And then, every other term keeps jumping and messing you up. So the alternating series has a very strict requirement. That is, the next term has to be smaller. Now, this is the test says that it starts at n has to be true for n starting at 1, but it doesn't. As we know, that series, being that we're talking about infinite series, the first finite number of terms don't matter, in terms of convergence or divergence. Okay, the first finite number of terms, even if there's a billion of them, they will all add up to be something, and they don't affect whether the series converge or diverge. So basically, as long as the bn plus 1 is less than bn for the tail end of the series, that's fine. Doesn't matter where the tail goes, but it has to fit the entire tail end. All right, so next let's look at example 5.19, which is a direct application of the alternating series. So please do convergence of the alternating series. So please do it as part of your homework. Next, let's consider the remainder of the alternating series. The remainder, it just means if we do the calculate the sum of an alternating series, and the best way to calculate it is just add up a finite number of sums, and that should be close enough, because the remainder, because what's left is not gonna be worth much. Now, but exactly how much is left, we can estimate it is this way. Okay, so then let's say call the remainder for the nth term. That is, if you add up all the way to n items, how much left that you are missing? The remainder is defined by, for example, well, the absolute value is defined by the actual limit minus the partial sum. Okay, which is and well, how do you calculate that? There is actually a quick way of seeing it. Is if you look at the previous page. Now, did I mention what page I'm on? I'm right now on page 499. The remainder calculation, 499. All right. So that if you look at the previous page, then we know how the remainder is calculated. Now the s, see, this is the first few terms, but you get the gist. See the s on the bottom there? Well, what is the s from the distance between s and any of the other terms? For example, what's the distance of s and s3? Well, it's less than b4. See, and then what is the distance of s and s2? That is less than b3, and so on. Because the way alternating series works, the difference is just going to be less than the next term. That is less than, yeah, whatever this is, bn plus 1. So the remainder, as we have seen earlier, the s get trapped in each term. Okay, once you move back and forth, the future is not going to get out of it. So each one becomes a new bound, new limiting area that the final limit can get to. So the remainder is estimated to be less than equal to simply the next term. See, piece of cake. So that's the theorem 5.14. And with that, please do example 5.20, which is a direct application of the simple remainder, n plus 1. And so I will write that down. Next, let's go to page 500, where we consider the concept of absolute convergence versus conditional convergence. Absolute convergence just means that if a series converges if the absolute value of all its terms put together converges, whereas it conditionally converges if the series converges but the absolute value of all the terms don't converge. For example, well, the harmonic series again comes to mind. Harmonic series, as we know, does not converge. However, the alternating harmonic series, once you arrange some of the signs, then it does converge. So that is the difference. That would be anyway. So the next theorem we look at 5.15. When a sequence converges absolutely, then it converges. Okay, no matter what the sign does. So that is a useful trick if you have well, I don't know how useful that is, but it is a trick. Now, the proof of that is very short and straightforward, so please do that as part of your homework, proving that absolute convergence implies any convergence, conditional or otherwise. So so next, example 5.21, and please do example 5.21 as your homework. There's more series to be worked on, and to check whether something converges absolutely or conditionally. Next, we are going to look at something weird. Okay, so far we have proved that the alternating harmonic series is one of those things that's converge conditionally, because if you get rid of all the signs and make everything positive, then it diverges as the regular harmonic series. Now you might wonder, and we care about that, why what's so conditional about it? It converges, doesn't it? Here's the interesting point, okay, is that it converges, however, but if you rearrange the way stuff is added or subtracted, then you can change how much this add up to. That is, it converges. You can get it to converge to a different value, or even get it to diverge. I mean, normally in a regular math, we know that if you add and subtract, doesn't matter which way you add it, right? You can, for example, add this first, or subtract that first, and then subtract this, and that. And as long as the number of stuff you're doing is finite, it makes no difference which way you do it. But in the infinite series, it actually makes a difference, as we're going to show it right now. Right now, for example, that we're going to prove that by rearranging things, we can actually get the alternating harmonic series to diverge. And here's the trick of how to do it. First, we consider all the odd terms, I guess. When I say odd terms, I mean the terms where the denominator is odd, such as 1 plus, we'll figure some number. We'll make it such that we'll add 1 plus 1/3 and 1/5. Okay, that's part of it, right? We'll add up only the positive terms all the way up to something that 2k minus 1 will make it bigger than 10. All right, so we'll add these things first. We're still subtracting the 1/2, whatever, later. But we'll add enough, we'll get to k first, where this sum is going to be bigger than 10. And then, so we can do that because the odd terms is a type of harmonic series. And this sum does go to infinity, because, yeah, it's very similar. And I think we might have done it, that this is this by the limit comparison test or something. This is the limit of this series compared to harmonic series approaches a constant. So then this series diverges. So if it diverges, then we can add up enough stuff so that it's bigger than 10. Might take a billion, might take longer than humanity exists or something, but heck, it will get to 10, right? Eventually. But anyway, so we do that, and then what we're gonna do is then we'll minus 1/2. Okay, we'll allow the first minus 1/2 to get subtracted, and then, oops, what's wrong with my marker? Okay, and then we're gonna, the next step is and then we're gonna add more stuff so that this thing, so from this point, after we subtract 1/2, we'll add more stuff to it. So then the whole thing now has to be, you add even more. How do you say add more? Okay, you just keep adding. Okay, you keep adding odd terms. So you keep add, I don't know, 2k plus 1. So after that is minus 1/2, 2k minus 1, and you keep adding odd terms, only odd terms, 2k plus 1. You keep going until this whole thing now is bigger than 100. All right, which will take, who knows, it takes when the galaxy might have expired. So at that point, you allow yourself to subtract 1/4. As you can see where I'm going. In other words, I'm doing all the addition. I'm just slamming on, just doing a ton of addition and doing the subtraction later and later. Now, if I do that, then as you can see, the partial sum is going to go to infinity, right? If I were to do that is I'll push back all the subtraction and procrastinate the subtractions much later. And not just that, I continue to do things later so then my sum will eventually diverge. And all that happened even though we just proved that the alternating harmonic series converge, but that's only if we add things obey the rules and add things like we're supposed to, subtract, add. If we so much as change the order, this thing will diverge. Isn't that neat? That's why it's called converging conditionally. The condition being that we gotta add it like we're supposed to, otherwise it might take off. just because of the order of addition that you're doing. So which is very, very neat. Now in reality, the book mentions that we can get the alternating harmonic series for give me a second, let me see. But in general, we can actually make the alternating harmonic series to sum up to be equal to any number you want. Now, isn't that neat? However, that is not so easy to prove, so we're going to skip the proof. And there's one more point we want to make is this rearranging series to make it equal to something else only works if the series converges conditionally. If it converges absolutely, then no amount of rearranging is going to change anything, which makes sense, but the proof, again, is very hard, and we're going to skip it. In fact, I don't even remember ever studying that myself. But anyway, so we're going to move on to example 5.22. Now that is a demonstration of how to get the alternating harmonic series to equal to something else, okay, which is very neat. So we're going to look at it. First, we are going to accept the fact that the alternating harmonic series equals to some value, and that it equals to natural log of 2 if you do it by the rules. That is, you add and subtract like you're supposed to. That is, we're not going to prove that right now and just accept that as a value. Yeah, we can prove that some other time. When I think we need need to learn a little more about this type of thing to be able to prove it. But right now, that's not important. Let's just say that equals the natural log of 2. And then this example, and what we're supposed to do is add and subtract a different way, push stuff back, forth, whatever, so that we want the series to become 3/2 natural log of 2. And we have to be able to prove it. So if we add and subtract, figure out a way to add and subtract it. Is this zooming in? Yeah. Okay. Then it needs to be some other value, 3 natural log of 3/2 of what it was. Now, how are we going to do that? So the book shows a simple way of doing this thing. So first, we have the original harmonic series, all right, which is written out here on top. Well, so far so good. Okay, here's the original series, and then next we are gonna take half of it. And well, half of it is then all the terms are gonna be even. Let's see. Okay, and why is this blinking? Not sure. Maybe my camera focusing is going nuts. Okay, anyway, so we'll take half of it. That's still so far so good. And then the next trick is more interesting, is we're going to create a new series that's identical to the half of the alternating series, but we're going to stuff in a 0 every other term. So then it lines up with the original one. See, so that 0, there's 0, 1/2, 0, 1/4, 0, 1/6. So what it used to be the odd denominators, now it has zeros. All right. So that sum, of course, then equal to natural log of 2 over 2. I don't know why my camera is blinking out. Maybe I pull back a little bit or too closer. Or maybe my camera is dying. Who knows? Anyway, so we have that series. So far, so good. And of course, if you add up those two series, then you got natural log of 2 plus 3 plus half of it, that's 3 halves, which is what we wanted. However, that is not good enough. We have to know that, but well, that's cute, but do we know that those two add up to be the alternating harmonic series, or they're just some random junk, right? So we're going to add them up, and if you look at how the book added them up, it doesn't make a whole lot of sense. So it doesn't mean anything to me. So I drew it out. See, here's why I drew out, and you can draw the same thing, and then it gets much clearer. That is, AN, the first column, let's see, I'll hold it here. The first column here is the original alternating series going down, right? And then BN is the new one that we take the original one and then, I don't know, divided it by half. Yeah. So, and then stuff zeros every other term. So the BN line up like this. So BN line up with all the even terms. See, all the even terms are the same, whereas the odd terms are all 0. See, the even terms, are they the same or opposite? The even terms are sometimes opposite signs, that is minus 1 6 plus 1 6, and then sometimes the same, that is minus 1 8, and then A is minus 1 8, and B is also minus 1 8. So you can see that they both follow a very distinct pattern. And then the B term, the way it works out is, look at what happens the third column where they add it together. So when they add together, then you have, what happens is you have, look at the odd terms, 1/3, okay? 1/3 still lines up with AN 1/3. 1/5 is lined up, right? Basically all the odd terms, all denominators are lined up properly. However, the even denominators is the first one got subtracted out, and then the next one then got added together to become the first term. See, and similarly, see, minus 4 is end up appearing where minus 8 was supposed to be, and so on. See, minus 1 6 end up where negative 1 12 was, and so on. So as you can see, while the odd terms were supposed to be in the final column, this one here, the even terms got pushed down by the double. That is, and yeah, 1/4 went to the 8th position, right? 1 6 went to the 12th position, and 1/8 went to the 16th position. But however, it's still the alternating harmonic series, though. It's just that as it works out, it just happens that the odd terms stay, whereas the even terms all got pushed back by the double. So each number got pushed back like twice as far where it's supposed to be. And just by doing this pushing back, as you can see, that is still the alternate series, because both odd terms and even terms are accounted for. It's just the even terms all are forced behind. Okay, and just by forcing that behind, this sum will add up to that, whatever that, 3/4 natural log of 2 instead of natural log of 2 like it's supposed to. And yeah, this just happened to be pushing back. Doesn't that look super neat? And you might think, how they come up with this trick, the BN, and then you divide it by half and add or something, and happens to be the alternate series again, except the even number push back. That I don't know. I think you just sit there one night with nothing better to do, and then you mess around with it, and suddenly know, oh, check this, it works out. That's I suspect how this kind of stuff is invented. Okay, just messing around, and it's like digging randomly and looking for gold. Sometimes it works. So anyway, so that's example 5.22. All right, so that marks the end of the section. Now, I would also like to mention that as we go further and further into the calculating series, it might be worthwhile to pull out all the series tests and definition and that sort of stuff, and put them all on one page, which I will do next time. And because there's more various things, and they have to be followed. A lot of times they have to be followed exactly right. So you don't want to such as, for example, the limit test is AN over BN, and then BN is this way, and then if BN converges, and then AN is something. So I think it's good if you put all that stuff on one page, okay, and in a shortened form so they all fits. Then and then when you do the series homework, to refer to them so that you do not make a mistake in applying any of the tests, and also to remember what the tests are. See that may one thing you might have to use a p-series, the other one use the limit comparison, and there's also the integral test, and so on and so forth. And of course, there's the divergence test to start with. If the sequence doesn't converge, you don't even have to think about it. So all that stuff is piling up. So please make a summary sheet of all those things. And then when you do your homework, keep the summary sheet next to you. Then things will be much clearer. I will get the homework done in the next video.